what we might call the real physics. So we're going to start with the branch of dynamics, and actually you will see that later when you do the problems, you will do also something which is kind of a subset of this, which is statics. But today mainly we are going to try to describe the motion of objects. So that's basically where usually you start out in physics. Try to describe the motion of objects, and then only later do we try to figure out why the object is moving and how that object is motion of that object is modified by different kinds of forces, which you will learn in about 2 more weeks. So this is the branch of physics involving the motion of an object and the relationship between the motion and other physics concepts. But by other physics concepts, basically we mean where the forces are coming from. So I like this to show this video from a long time ago. This was when I was really young and we used to watch the Olympics. If you have, some of you have watched high jumps in athletics. This is how people used to do high jumps at one point in time. Let's see. Have you ever seen people do high jumps like that recently? No? Because look at what the next athlete does. This is what is used these days, and the new one is called this. Current version is called the Fosbury flop, named after Mr. Fosbury, of course. So you'll see that this one is considered more efficient than the one going over the front. That's because slowly as you learn new concepts, you'll learn that in this technique, your entire center of mass of your body is actually going over the bar. Okay, in this case, not over the bar, but when it's trying to go over the bar, the entire center of mass is going over the bar. Whereas the Fosbury flop, this one, will when you learn about the concept of center of mass later, you will see that the center of mass is actually going under the bar in this case. So that's why this is actually a more efficient method, and after this technique was used, the world records and everything started going up very rapidly. So, of course, we are not going to we are going to deal with those concepts in the next few weeks. But today, we are going to look at something called kinematics. I wanted to give you another example. This is, I believe, this is a machine which is doing with which you can do brain surgery. So one reason we first emphasize a lot about things like position, displacement, time, and all that, velocity, is that even in a machine like this, you will actually have to figure out, okay, that this is my coordinate system, this is what the brain looks like under the microscope, this is where I want to go and operate. So what direction should the machine that is doing the actual operation, which direction should it move? In this machine, actually, most of the surgeon himself or herself does not really go into the brain with scissors or anything. I don't know anything about operations, that's why I'm using scissors. But what I'm saying is that the devices used by the machine, the operator is just sitting at that machine and trying to figure out, telling the machine where to go. So things like the position and at what speed to go and how fast to go, at what rate of speed. What I'm trying to do is avoid the term acceleration before I actually define it. But at what acceleration should it go to a certain part of the brain? So for all these things, you need to have some kind of innate feeling about all these quantities that we are going to learn today about position, displacement, velocity, and acceleration. So this is the field of kinematics. It is a part of dynamics, which I talked about before. And in this case, we are only interested in the description of the motion, not in what is actually causing the motion. So that will come later when you learn about forces. So today it's only kinematics. So again, remember there are no points for HITT questions this week also. One thing I don't think we've mentioned during the syllabus is when they do start counting, if you don't respond at all, it's 0 points. If you respond when the answer is incorrect, it's 1 point. And if you respond and the answer is correct, it's 2 points. Okay, so I don't think we mentioned that when we were discussing the syllabus. But today again, I'm just going to do these problems as a test of your clickers and of course, as a test of to get some feedback from you. So these are the instructions for logging on and tuning your clicker to the frequency out here. Okay, so the first question is going to be, so the first question I'm going to show you on that side, and this is without knowing any of the math that you're going to do later. This is just what kind of innate feeling you have about how things move. So the question is, you can stop your car within 10 feet when you're driving at 20 miles an hour, like the speed limit on campus. Under similar road conditions, let's say you are not driving at the speed limit, let's say you are driving at 40 miles an hour on campus, don't do that. But if you are, and that's the reason why you don't drive at 40 miles per hour, but what is your stopping distance if every other road condition is the same, if you are driving at twice the speed? So your speed is double. What do you think will happen to the stopping distance when you're under the same road condition, same brakes, you brake exactly as hard in both cases? I'll start the time in a moment. So I'll give you 2 minutes to think about this one. And you can actually, since there are no points today, you can talk amongst each other also what you think about it. So that's the answer that you gave, and you can actually, this is kind of the reason I asked this question. Because the speed was double, you said that the stopping distance will also be double. What we will do today is show you the equations. Actually, the equations will come on Thursday, but today we'll set up all the foundation for figuring out those equations. The answer in this case is actually 40. So, so that's why, again, of course, this is not, the equations that we are going to do are kind of basically the first approximation of reality. But you will see that if you're driving at twice the speed, your stopping distance way more than doubles. In this case, you're saying that the stopping distance becomes 4 times what it was before, instead of just becoming 2 times. So what does that tell you? Your speed doubles, which means increases by a factor of 2, but your stopping distance increases by a factor of 4. So that means, in terms of mathematics, there's some kind of a square somewhere in the equation. Okay? So those are the things that we are going to cover today and on Thursday. So, of course, right now, I just told you that it's 40 feet, but the equations that we figure out will actually show you exactly why it's going to be 40 feet. Yes, so we'll get to that. So in this case, the answer was, answer was, what was it? D, yeah. Answer was D actually, so 40 feet. And again, I told you that I'm asking you this question without even telling you what the concepts yet, but we'll get to those in a moment. Okay, so now that we know that there are some things that are not exactly clear just from our intuition, let's go ahead and start defining some quantities. So the quantities of motion are, let me change this one. The quantities of motion that we'll need to define are displacement, velocity, and acceleration. So of course, velocity and acceleration you have heard before. Most of you use that. Although instead of velocity, most of the time we use the term speed. So displacement, on the other hand, is not something we use in daily life much. But in physics, actually, that is a concept that is more, sometimes quite necessary, maybe even more important than just the distance. So these concepts will be used to study objects in motion and come up with equations that will show you why that stopping distance quadruples instead of just doubling. So this is what we are usually used to talking about distance. But in this course, we'll first define displacement, and then I'll come back to distance again. So the displacement is defined as the change in position, delta x, where the delta x is the final position of the object minus the initial position. Graphically, we are now, this chapter, we are only going to do one-dimensional motion. So our coordinate system basically has just one dimension. I'll just draw the second dimension just because I feel really uncomfortable when there's only one horizontal line. But in this chapter, we are not doing two-dimensional motion. That will be the next chapter. So let's say we are moving along the x-axis, and there are some positions that are marked 1, 2, 3, 4, 5, and let's say these are all distances in meters. Let's say your object starts at this point. Can everyone in the last row also see these numbers? Is that okay? All right. So let's say this is where you start. So this is what you will call your initial position x naught. By the way, I'm going to use, this is too much like, I'm going to use this as my x. Why there's such a fancy x which looks kind of like a chi? Because you'll use this for multiplication sometimes. So not to get confused with that, my x will look like this. Alright? So x naught is its initial position. So 0 stands for initial. Sometimes you'll also see it's called x sub I. And this book uses, the book you're using uses x of 0, so x naught. And let's say the object goes from x naught to x final. This is its final position. For figuring out the delta x, the displacement in physics, whenever you look at the change for something, remember this, whenever it's change of anything, in this case it's the change of position, delta x, it's always the final value minus the initial value. Okay? So in this case it will be xf minus x naught. And that is, xf is 5, x naught is 3. Meters. So that's your displacement in this case. Displacement is in one dimensions also. It's actually a vector quantity. Of course, in one dimension that means it either points in that direction or it points towards the left. In this case, because the object is moving towards this x final, which way does the displacement point? It points in that direction. And that's why it's pointing towards the positive x-axis, and that's why it's a positive number 2 meters. Okay? Displacement could even be the other way around. Like, let's say I now go, I'll use some Blackboard PowerPoint to erase some of these points and make this your initial position. Let's say this is a new case. The object starts here and ends up out here. This is your final position. In this case, xf minus x naught will be, what will it be now? 3 minus 5, right? So you just, and this time it will be negative 2 meters. And that means, this time your object is actually moving in this direction. If the arrow points towards the left, and that's why it has a negative sign in front of it. We'll of course do real two-dimensional vectors in the as soon as we start the next chapter when things are moving in 2 dimensions. So displacement can be both positive or negative. If the object is moving only in one direction, in both these cases, either it was moving only towards the right or it was moving only towards the left. In both these cases, if you just take the magnitude of the displacement, that comes out to be 2 meters. If the object is moving in only one direction, the magnitude of the displacement is equal to the distance. Okay? So the distance is the same as the magnitude of the displacement only if the object is moving in the same direction throughout. I'll tell you why that is, why I have to specify that. That's because, let me raise this one a little bit. Let's draw another x-axis. And again, 1, 2, 3, 4, and 5 meters. Let's say the object this time starts at x naught here, goes all the way to 5 and then comes back. Okay, so goes in that direction but then turns around and comes back. What is the displacement in this case? 0. The x final is here, 3. x0 is also 3. So your displacement in this case is 0. Okay? However, the distance that you covered is not 0 anymore. Distance that you covered is actually 2 meters going that way, right? And since distance is a magnitude of that delta x, you also add up 2 meters coming back. So the total distance in this case We'll usually call it v. So although the displacement was 0 meters, the distance is 4 meters. So if it is moving in the same direction, you can just use the magnitude to get the distance. But if you're moving in changing direction of motion, then distance has to be calculated that way. Basically what you do is take the magnitude of the distance while it was moving in one direction, and then stop. Take the magnitude of the direction again when it's moving in the opposite direction, let's say, and then add them up, and that will give you the total distance. Okay? Questions about distance and displacement? All right. So next, we introduce the term, the velocity. So it takes time for an object to undergo the displacement. It's not going there instantaneously. So the average velocity is the rate at which this displacement occurs. So it's denoted by v with a bar on top of it. Delta x is your displacement, xf minus x0. Delta t is your change in time, which basically means that it had this position x0. Let me go back to this drawing up here. It had this position x0 at a time of t0, and it had this position xf at a time of t sub f. So delta t is your final time minus the initial time, just like your delta x is your final position minus initial position. So, and you divide the two, delta x over delta t, that gives you the average velocity. This is a vector quantity. That means it has direction. Because it is a vector quantity, why does it have direction? Because displacement has direction. Okay? So if your displacement is pointing towards the right, or in this case your displacement is pointing towards the left, then your velocity is also pointing towards the left. It has the same direction as the displacement. Alright? So that's a vector quantity. The thing that we are more familiar with is the term speed. So if the previous one was average velocity, average speed is actually not, again, just like the distance is not always just the magnitude of the displacement, average speed is not always the magnitude of average velocity. If it was moving in the same direction, the two will be the same. But if they change direction of motion, the average speed is the total distance divided by the total time. So you divide d by your delta t. I should have written delta t out here. It's d over delta t. Alright? And for the lack of any other symbol, I've just put v out there without the bar on it. You can decide what kind of symbol to use for speed. Speed, because it's the magnitude of the total distance over total time, is actually a scalar quantity. Okay? So that's the difference between velocity and speed. Soon you'll see that this difference is only there because we are talking about average speed. When we go to instantaneous speed, the things will actually get a little bit simpler. So if your average velocity is constant, here are 3 graphs I've taken from the book, and I've hidden the right part of it because there the position, the direction changes, of motion changes. So let's say you're moving in the same direction at a constant velocity. Your position versus time graph is going to look like a straight line. So let's say your initial position was 0 and your final position in this graph is 3. And it takes about less than 0.3 hours to reach there. Okay? So that straight line tells you that you're moving in the same direction. You're always moving in the positive direction at a constant velocity. How do we know it's constant? Because the velocity is actually the slope of that graph. The slope of that graph, of the position versus time graph. I think there's a pointer up here. can hardly barely see it here. So that, the top graph, which is the position versus time graph, should be a straight line if your velocity is a constant, because velocity constant means that you're changing position at a constant rate. So if you take the slope of that graph, it gives you a horizontal line, which is the velocity versus time. Okay? So it's a horizontal line is the slope of that graph. And you can see that as long as it's moving in the same direction, your speed is just the magnitude of your velocity. That's also a horizontal line, and it's exactly the same as your velocity in magnitude. Questions about these three graphs? What I want to show you is when the velocity is not constant. And that is, I take away those squares. Now let's say the position starts changing in the other direction. And you can see immediately that the slope of that graph, the position versus time graph, the slope is now negative, right? It's pointing this way. So your velocity, which is the slope of the position versus time graph, becomes negative. Does that make sense? It was positive and constant, and then it switched to negative and constant. All right? However, look at the speed. The speed remains the same in both cases because it's you take the magnitude of the velocity for the left part and the magnitude of the velocity for the right part. The speed, average speed, remains the same throughout this whole motion. Okay? So it's basically saying that if you're driving at 20 miles an hour from here to the Century Tower, let's say, your speed is 20 miles an hour. Then you come back from the Century Tower back to the physics department, your speed is still 20 miles an hour. In both cases, your speed remains the same. But your velocity while going towards the Century Tower, let's say that's your positive direction, you're going away from physics, so it's positive. So that's why that becomes plus 20 miles an hour. When you return, it's negative 20 miles an hour. All right? So that's your concept of average velocity. Now, we are going to look at this non-constant velocity a bit more in detail. So this is, in this case, the position versus time graph. The position is always changing in the positive direction. So you're not really changing direction in this case. So your velocity, the slope at each point of that graph, the velocity remains positive, right? It never changes direction, the slope never becomes negative. So, if you want to figure out the average velocity for something like this, which is not a straight line, the average velocity is that you join the endpoints by a straight line. You cannot see the delta t. You join the endpoints, your final position and your initial position, join those two by a straight line, and and figure out the slope of that one. So the slope of that blue line is delta x over delta t. And from your definition of average velocity, delta x over delta t is your average velocity. So it's the slope of the blue line joining the endpoints. So do you see the difference between the two? In the case of constant velocity, it was a straight line, the position versus time graph, so the slope never changed. In this case, the slope is changing. So what you do to figure out average velocity is just join the endpoints and figure out the delta x over delta t. That's your average velocity over this entire trip. Okay? So average velocity has a problem because, of course, it's not clear in this case. But look at this case, for example. In this case, your delta x was 0. You started and ended at the same point. If you try to figure out the average velocity for this trip, what would your graph look like? Your graph would look like position x versus time. Your graph would look like, let's say, some kind of curve you go from x equals you went from x equals 3 to x equals 5. Okay? I'm not assuming that it went with constant velocity. Then it reached there and it came back again to a position of 3. So your initial and final positions are the same. To figure out the average velocity, which point should I join with the blue line in this case? This point out here, and join it to the initial point out here. What's the slope of this horizontal line? It's 0. So the velocity, average velocity in this case turns out to be 0, which doesn't really give you much information because it just tells you you came back at the same point. It didn't tell you at what speed you drove to the Century Tower and or what speed you came back. So that's not that useful in certain cases. So that's why we introduced the concept of instantaneous velocity. The instantaneous velocity is basically the same delta x over delta t, but you now reduce your time interval to as small a value as possible. Now again, we are avoiding calculus in this course, so I'm not going to give that delta x over delta t limit, delta t going to 0, a specific name, which most of you know, but I'm not going to mention it. So what we are saying is that we are getting the time interval to the smaller and smaller values. And eventually, when the time interval is really small, that is basically your instantaneous velocity. The instantaneous velocity indicates what is happening at every point in time, not just at the final time and initial time. You are also trying to figure out what's happening in the middle out here. So graphically, what that looks like is this. You start with your definition of average velocity. The slope of the blue line is delta x over delta t, that's your average velocity. Start reducing your time interval to smaller and smaller values. So when it approaches 0, delta x over delta t is the slope of this curve just at that point where you are trying to measure your instantaneous velocity. So my blue line in this case has a slope like this. Okay? So as I go along that red curve, the slope of the blue line is going to change, and that is your instantaneous velocity, the slope of the red line at each instant of time. Questions? So that's your instantaneous velocity. The average velocity was when you were only taking the end points of your trip into consideration. Yeah. So instantaneous velocity, so average velocity is this. Let's call it V average is equal to delta x over delta t. V instantaneous is just that you take the limit of the average velocity with delta t going to 0. And that is your V. So it's the average velocity, but when the time interval goes to almost 0. Okay? So that's your instantaneous velocity, which is defined as the slope of the position versus time graph. So if you are given a position versus time graph, and you are asked, okay, what is the speed? What is the instantaneous velocity at time some t, which I mark at this point out here. What you do is, for that time t, figure out which part of the curve that corresponds to, okay, and then find out the slope of the curve at that point. All right, and that is your instantaneous velocity. Now, instantaneous velocity has another nice feature, and that is instantaneous speed is just defined as the magnitude of the instantaneous velocity. You could not do that with average velocity. Average velocity's magnitude was not always the average speed, but instantaneous velocity's magnitude is always the instantaneous speed. Okay? So the slope of the line tangent to the position versus time graph is defined to be the instantaneous velocity at that time. That's what I told you just now. Questions about that? Okay, time for a problem. So the problem is this. flagpole. Now when you see problems like this, so this is my flagpole. I'm not saying when you see problems like this, you have to draw a flagpole. You have, what you have to do is decide that, okay, this is the origin of my problem. Okay, the origin means this is my x equals 0 point. What it says is, runner A is initially 4 miles west of a flagpole. So just because we are used to maps, we are going to consider west to be on the left hand side of the origin, and that is 4 miles. Okay. So this is runner A. And runner B is initially at 3 miles east of the flagpole. So runner B is here. So then it says runner A is now starts running with a constant velocity of 6 miles an hour due east. So that means runner A is moving in this direction at 6 miles an hour. Okay, and runner AB is moving. Runner B is running with a constant velocity 5 miles and 5 miles an hour due west. So runner B is running due west at 5 miles per hour. Okay, so they are of course going to meet somewhere. The question is, where are they going to meet relative to the flagpole? Okay, so some of you have done problems like this, usually with trains or something like that, but we are going to do it systematically with our definitions of velocity and everything that we just learned. So I'm going to ask you 2 clicker problems, and they are very short clicker problems, so that's why I'm only going to give you 1 minute for each of them. So the problem is this. If both runners start at the same time and meet at a point X, so let's call that point let's say they meet at this point X. Okay. So they are running and they meet. Remember, I'm not taking into account anything. So we are taking into account anything that will prejudge. So with which I prejudge which side of the flagpole they're going to meet. I'm going to just say that they're going to meet here on this side. You'll see that the math will tell you whether that meeting point is on this side of the flagpole or on this side of the flagpole. You don't have to decide it right now. You just put some arbitrary position X anywhere along this horizontal line. So the first question is, if both runners start at the same time and meet at the point X, and runner A takes time TA to reach point X and runner B takes time TB to reach point X, then what is the relation between time T sub A and time T sub B? I'm only going to give 1 minute for this one. So they both start at the same time and they meet after time PA and PB.
In the beginning, he was like, oh, this is still not great.
What do you think?
Okay, so they both start at the same time they start running and they meet. Okay, so that means when they meet, they have spent the same amount of time running. Does that make sense? That both of them start at the same time. Both of them have stop clocks. Okay, and when they meet, they stop those stop clocks. You'll see that okay, they both have the same time on the stop clock. Is that clear why they both have the same time? No. So I start running and you start running at the same time towards each other. We have clocks in our hands. We both start the time interval at the same stop clocks at the same time. When we meet, when we pass each other, and we stop the stop clocks because we are meeting exactly at the same time for each other, right? So it's the same time. Does that make sense now? I mean, there's a few ways I can say this, but another way of explaining it? No? So I'm believing, try this experiment out maybe later, that you start your stop clock at the same time and start walking towards each other. It will show you the same time when you meet. Okay? Alright, so the two times are the same. So TA is equal to TB. So that's what we are going to use to solve this problem. Let's call TA, T sub A, and T sub B, both are equal to each other. Let's call them both of them equal to T. So, what is the velocity of this runner A? Runner A, in terms of your delta x over delta t, what's delta x for runner A? His final position is x. What's the initial position? 4 minus, right? But it's in the negative side of the origin. So this position is actually negative 4 minus. Okay? So for runner A, x minus, so final position minus the initial position. What's your initial position? Negative 4. Divided by the time that interval that has passed, t, and that is equal to 6 miles per hour. So that's your velocity equation for runner A. Is that, so runner A. Is that clear why for runner A this is the equation? It's delta x, delta t equals velocity, average velocity. Alright? So that means, of course, this one is out here is x plus 4. I take the 6 to the denominator, and that is my equation 1. X plus 4 over 6 equals t. I'll continue on this board. What's the same equation? Now I need you to shout out maybe. What's the same equation for, the same velocity equation for runner B? The final position for runner B is also, where is it? X. And the initial position for runner B is plus 3. So the delta x for runner B is x minus 3, delta x, over the same interval of time equals 5 nt. So there is one of these equations still has an error actually. And that is my next clicker problem, and I'm going to give you again 1 minute for that one. What are the velocities of runner A and runner B respectively if vectors pointing to the right are positive and vectors pointing left are negative? Okay, so that is correct. So this velocity is positive because it's pointing right, but this one needs a negative sign in front of it. Okay, so this one will give you an equation x minus 3 over negative 5 is equal to t. That is equation number 2. How do you solve these equations? You see that both the right hand sides of these two equations are the same. So you can equate their left hand sides. So that means you can write down x plus 4 over 6 is equal to x minus 3 over negative 5. Okay? Because the left hand side are equal.